In this video, we will be talking about physical properties of amides. That way we can predict the relative boiling point or melting point of amine and amide molecules, as well as describe the intermolecular forces between two similar amine and amide molecules or with water. So to get things started, do hydrogen bond intermolecular forces exist between two amide molecules? The answer to that is, well, let's think about that. We have our amide here, and so we have some lone pairs on the nitrogen as well as on the oxygen. And so as long as we have some hydrogens, we could have a donor. And so we can have hydrogen bonding for primary and secondary amines, but not tertiary amines. Tertiary amines have no amides. Tertiary amines have no donor. And so tertiary amides lack those hydrogens. These have yes. These were, that X was a no. And so since they do have hydrogen bonding, we know that all of our carbonyl functional groups are polar. So they will have dispersion forces, dipole-dipole forces, and hydrogen bonding. Do dipole-dipole forces exist between two amide molecules? Well, I just answered that. That is yes. All carbonyl functional groups are polar. And so since you have polar molecules, we will have intermolecular forces for dipole-dipole. All right, and then everything has dispersion. So yes, everything has dispersion. So let's think about, since we now just covered all the intermolecular forces, let's think about how we can rank our amides relative to other functional groups. Let's start off by comparing primary and secondary amides compared to tertiary amides. Primary amides and secondary amides will have higher melting points and boiling points because of the hydrogen bonding. So primary and secondary will have higher boiling point and melting point due to hydrogen bonding. Do primary and secondary amides have higher or lower melting points and boiling points compared to similar esters? Well, esters don't have any hydrogen bonding at all. And so primary and secondary amines will be higher. That was supposed to be have A. And so this is also going to say we'll have A. Higher boiling point, higher melting point due to hydrogen bonding. Do primary amides have a higher or lower melting point and boiling point compared to secondary amides? Well, see, now we're getting into some more nitpickiness. Both are capable of hydrogen bonding, but the primary has more hydrogen bonding because it has more hydrogens. Higher boiling point, melting point. More H's for hydrogen bonding. Do tertiary amides have higher or lower melting points and boiling points compared to similar alkanes? Alkanes have no hydrogen bonding, but they're also completely nonpolar. Nonpolar substances can only have dispersion forces. Tertiary amides have dipole-dipole. And so we will have higher, this was nonpolars as dispersion. And so since this is dipole-dipole, it will be higher. So tertiary higher than alkane. Now we can think about the solubility with water. And so now we have to think about the intermolecular forces between our amide functional group and water. I'm going to draw water with the H's sticking out. Can primary and secondary amide molecules hydrogen bond with water? Yes, they can. They can accept and donate. And so water can accept and donate, the amide can accept and donate, so they will hydrogen bond with water. Tertiary amides can also hydrogen bond with water. They can only accept. Water will donate. Are primary and secondary amides soluble in water? Well, yes, they can hydrogen bond with water, as long as the carbon chain is not too long. Carbon chain. So as long as the carbon chain is short. Once that carbon chain becomes long, then the nonpolar dispersion-only part of the molecule is overwhelming and hinders the ability for the molecule to form hydrogen bonds. Same thing with the tertiary, but we'll write yes, but not as much as primary or secondary. And then again, we have to worry about whether the chain length is short enough.